maybe some of you who attend the control class may already heard about the transfer function and may already familiar with the Laplace transform. But in our vibration class, the Laplace transform can also be applied to solve vibration problem. It's a good alternative. So today, maybe the Laplace transform and transfer function is still new for some of you today, and we're gonna begin from the basic and try to see how can we apply the Laplace transform for vibration problem. Last week, when we talk about the general force vibration, we try to introduce the concept of convolution integral, the concept of the impulse response, the concept of impulse response. Maybe we need to recap that we have a hammer and hit on a system, and a system vibrate due to the effect of just a short duration of time due to the impulse. And general force can be considered as infinite of impulse for a different point of time. Maybe general force can be a continuous force function, and at each point of time we try to use the impulse to capture the force at that time and consider the effect of that impulse with the magnitude of the force at that time. And when the time is going, when the time change, at the second point of time, we have another impulse function with the different magnitude of impulse, and the magnitude of the impulse at the second point of time gonna equal to the magnitude of the force at that time, and it's gonna create the vibration, the impulse response vibration due to the second impulse. When we have continuous time input, we're gonna continue with the third point of time, fourth point of time, and the total response due to a general force input gonna be the linear combination of each impulse response. So here's the concept. And today, in the first bullet, the concept we talk is the convolution integral, means the total vibration response gonna be the sum, the linear combination of each impulse response. So the convolution integral in the time domain can be simplified to be the idea of the transfer function that relate input and output. And today we're gonna see this between the time domain in convolution integral and in the Laplace domain in the transfer function. And when we introduce the Laplace transform, we are going to try to derive the Laplace transform of some basic function. Of course, the impulse input in time domain gonna be the basic one, and followed by the step function, the ramp function, impulse function from last week. Last week we have the impulse function, right? And impulse function is the function that the impulse function is a function that have the value only at that point of time, and the integral of the impulse function, the unit impulse function, the integral from minus infinite to infinite of the function against time, the area under the plot of the Dirac delta function against time, the value of the integral gonna equal to 1. Here is the impulse function. The step function is the function that change its value at a point of time when t equal to 0. It change the value from 0 to 1 is the step function. The ramp function gonna be the things that increase the value when the time increase. And the slope for a unit lamp, the slope gonna be 1. The slope gonna be 1 for a unit ramp. For unit step, the step size is also equal to 1. Unit impulse or the Dirac delta, the value of the integral, the area under the plot here equal to 1. Exponential decay. Many times when we derive the response of vibration, we're gonna see something like e power minus psi omega nt cosine omega dt, something like this, which means the response of the vibration like this gonna be cosine function with the omega d, means the cosine omega d, the omega d give the idea of the period of the vibration. And of course, the vibration have only one omega d. It will continue vibrate with the omega d, the damn natural frequency. But the magnitude of the vibration, the free vibration response, the magnitude of the vibration in the underdamped case, the magnitude of the vibration gonna decay with this function, depend on how big is the damping ratio, how big is the natural frequency, but the magnitude gonna decay when the time pass. So when we derive the free vibration response by our technique that we used in the previous class, we saw that the response contains of two parts, the part of sine and cosine, and the part of the magnitude that decay against time. So today, we may see how the decay, the exponential decay function can be converted between the time domain and the Laplace domain. Actually, by definition of the Laplace transform, the exponential decay is one part that contained in the calculation process for the Laplace transform. So we're gonna see it today. And of course, the part of sinusoidal function, we also need to be able to convert between the time domain function and the Laplace transform of cosine and maybe sine function. We need to be able to compute the Laplace transform of the exponential decay, Laplace transform of sinusoidal function, Laplace transform of unit step, ramp, and also the delta function. And when we need to apply, when we can, of course, we're gonna have a question why we need to derive the Laplace transform of a function. To obtain the Laplace transform, of a function, you need to do the integral of that function multiplied by e power minus st dt. And it seems like we need to perform the integral process, and it's not easy sometimes. So we need to spend effort to compute the Laplace transform, but we should have something as a reward from the calculation like this. Laplace transform should have some advantage or benefit over the previous method we studied. So in order to show how powerful of this method, how simple of this method, we're gonna see when we need to apply the Laplace transform technique for the overdamped free vibration and underdamped free vibration. And also we have one MATLAB example at the end of today's class. MATLAB example means maybe when we need to plot a vibration response of a system, we can simply put a code in MATLAB in field command line, and we can plot the result we're gonna see as a tool. So recap the idea of the convolution integral. We should begin from maybe a general force function. The force may vary against time. And another function that is important is a delta function. With a time shift. A delta function with a time shift tau means the value of the function gonna be 0 when the time is not equal to tau. And when the time equal to tau, the function will have value. But we don't know the magnitude. of the delta function. But by definition of the delta function, what we can know is the integral from minus infinite to infinite of a delta function. Direct delta function, the area under the plot gonna equal to 1. But we don't know the peak of the delta function. And when we need to capture the value of a function, when we at this point of time tau, the value of function, I I need to wait a second. Maybe I should introduce the convolution integral. A response, a total response is equal to the integral of force magnitude at time tau multiplied by impulse response at that time shift d tau. Okay, let's begin from this. I'm gonna explain this equation. This equation by the math operator xt is equal to force convolution with impulse response. Y xt is equal to the integral of f tau multiplied by the impulse response at that time shift. The response, vibration response, force and impulse response, vibration response, total vibration response, a force function, and impulse response. We begin from this line. A response equal to a force convolution with impulse response. Force function depend on the function of the force. It can be step function, ramp function, sinusoidal function, or any continuous time function. Impulse response is a system property. Impulse response is a system property means if a system have mass, have spring, and have a damper, and we hit the system with a hammer, when we hit the system with hammer and the force just apply as a unit impulse direct delta when time equal to 0, the system gonna vibrate. When we hit it, what we create is the initial velocity. Initial velocity means the initial slope when time equal to 0. The response due to the impulse input is impulse response. Impulse response have initial slope and then continue vibrate. The shape of the response, the shape of impulse response depend on natural frequency, damping ratio, natural frequency. And natural frequency, damping ratio, and natural frequency depend on M, C, and K, the parameter in the system. And system property. So the impulse response is the thing that explain a system property. If we hit the system with a hammer, with a direct delta function, direct delta or unit impulse, how the system gonna behave, how the system gonna vibrate by just a direct delta input. So the system gonna vibrate and show its property, show their omega n, damping ratio, and omega d in the vibration. But in this case, the input is just an impulse response, just an direct delta function when time equal to 0. But I already mentioned that for a general force response, we may need to use a unit impulse when time equal to 0. And when we multiply by the value of function, we're gonna have the impulse response at that point of time. Here, the input is direct delta. Magnitude of direct delta is equal to 1. But at that point of time, if the value of the function is not equal to 1, if the value of the function at the time tau is not equal to 1, the impulse response due to the force that the magnitude is not equal to 1 gonna be the same shape with the vibration that have the impulse response, but just multiply by something that extend the magnitude. The magnitude depend on the size or the magnitude of the force that if we have a direct delta input, we should have a pair like this. If the input is a direct delta, output gonna be an impulse response. If the input is the magnitude of the force at that time, multiplied by a delta at that point of time, output gonna be the same, but multiplied by the force magnitude at that point of time. So the magnitude of the force at that point of time just affect the magnitude of the impulse response. Unit impulse response. If the input is direct delta, output of vibration gonna be unit impulse response. If the input is something constant multiplied by a direct delta function, a constant just multiply as the magnitude, multiply to the magnitude of a unit impulse response. But the omega d, the omega n the natural the damping ratio still remain the same as a system property. We just multiply the magnitude of the force to the unit impulse response. And as I mentioned that when time equal to zero, if we have direct delta input, we're gonna create a vibration due to a direct delta input. But if the magnitude of the force is not equal to 1, if magnitude of the force is not equal to 1, the magnitude of the impulse need to be multiplied by the force at that point of time. Maybe we need to multiply by F when time equal to 0 and have the impulse function. When we have impulse when time equal to 0, the vibration gonna be impulse response, but need to multiply by the magnitude of the force when time equal to 0. When time equal to tau, what gonna happen when time equal to tau? When time equal to tau, the force at that point of time also create a vibration. And the impulse response is simple. It's just a impulse response with a time shift. If direct delta apply when time equal to tau, impulse response gonna begin from time equal to tau. How about the magnitude? Of the impulse response? Magnitude of the impulse response gonna be the magnitude of the force at that point of time. So for each individual impulse, it's gonna create one impulse response multiplied by the magnitude, depend on the size of the force at that point of time. But the total response, if you need to find the total response at any point of time t, you need to consider when the tau equal to 0, when the tau change to some value, until when the tau equal to the time t. And the response gonna be the linear combination of all impulse response. It means if you need to know the total response at time t, you need to consider magnitude of force at time tau, begin from when tau equal to 0 until tau equal to time t. Magnitude of the force multiplied by a unit impulse response, with the time shift tau. For example, when time equal to 0, we're gonna have force when time equal to 0 and impulse response with the time shift equal to 0, with the time shift equal to 0. And we have one vibration response. When the time equal to 0.01, you need to find the magnitude of the force at that point of time. And the impulse response at that point of time means the impulse response, unit impulse response with the time shift. But here is time equal to 0, time equal to 0.01. You need to sum this until when the time equal to the time t that you want, time t that you want. At time t, you need to integral from when time equal to 0, and you change the value of the tau from 0 to time t. The running parameter is tau. The running parameter is tau. And the limit of integration from 0 until the time t, until the time t. And by the concept, I would introduce a kind of block diagram. You can see that the system itself have the impulse response as the system. When we need to explain a system, we can explain it by impulse response, HT. The impulse response depend on the system property, omega n, damping ratio, omega d. Impulse response by the physical meaning means if we have one vibration system and we hit it by a hammer, how it's gonna vibrate? By a unit impulse input, by a direct delta function. It's gonna show the system property. Natural frequency, damping ratio, damp natural frequency depend on the parameter MCK of the system. If we change the magnitude of the input, the magnitude of the input will perform the convolution integral with the impulse response function, and we're gonna have the response as output. Here is in time domain, but in the Laplace domain, the thing gonna be simple. The force in S domain, the system transfer function, the output in the Laplace domain. In the control class, we know that the transfer function of the system is output divided by input. Transfer function is output divided by input. But the new conclusion from today is a way to obtain a transfer function is to apply a unit impulse to the system and see how it vibrates. By experiment, if we can control the unit impulse input and the system have MCK property, when we see it vibrate and see the decay of the magnitude, we're gonna have idea of omega n and the damping ratio And of course, when we observe the vibration, we have idea of the omega d. We can have experiment for physical system, and we can obtain the transfer function by experiment, and we can predict if the input is not direct delta function anymore, how the system gonna behave, So here are the rough idea about the convolution integral that relate the general force input and the general force vibration response xt to the direct delta function, and give introduction to a transfer function. Before we see an advantage of the Laplace transform and transfer function, let's try to derive Laplace transform for some simple example. When the function is direct delta, the Laplace transform of a direct delta function, the Laplace transform is the integral from 0 to infinite of e power minus st and function in time domain and dt. Wow, is this difficult to do? We are maybe we still lucky. The value of the function delta, the value of the function gonna be 0 except when the time equal to 0. And I think we should know this property. When we have a force function multiplied by a direct delta, maybe with a time shift, by definition of the direct delta, the direct delta gonna have the value only at that time point, and the magnitude of the integration for direct delta against dt from minus infinite to infinite of a direct delta function, the area under the plot, the area under the plot gonna equal to 1 for direct delta function, and this one is useful. The value of direct delta gonna be 0 except at one specific time point, and the area of integral is equal to 1. Which means if we need to have the product of the force multiplied by direct delta, the value of this product gonna be 0 everywhere except at the time point equal to tau. this one we can take the value of the function at that time shift, because the integral of delta dt equal to 1, and the function when it multiply to direct delta, it's gonna be 0 everywhere except at that time point. Actually, this one can explain, maybe somehow can explain this, but for here it can like clearly be seen that we need this property, because when we need to obtain the integral of the product between e power minus st and the delta function when time equal to 0, everywhere the value of the product, everywhere it's gonna be 0 except when time equal to 0, e power minus st gonna have a value. So this integral is equal to e power minus s, and when time t equal to 0, it have a value. So the Laplace transform of a direct delta function is equal to 1. And what should be next? How about the step function? The step function Laplace transform of a unit step function equal to integral from 0 to infinite of e power minus st and the function and dt. A step function have the value 0 and 1, right? A step function. So the Laplace transform of a unit step function. So the limit of integral is from 0 to infinite, and the step function itself, have value equal to 0 when time less than 0, and have the value equal to 1 when time more than or equal to 0. So it's nothing here. Because the limit of integral, we consider only the positive region, and the unit step function with 0 time shift itself gonna be 0 when time less than 0, and gonna be 1 in the positive region. So the integral here, we need to just obtain integral of e power minus st. Integral of e power minus st dt is e power minus st divided by minus s, and the limit of integral from t equal to 0 to t equal to infinite. So the Laplace transform gonna equal to, when we consider this one, it's gonna be 1, maybe minus 1 per s and multiply by 1 per e power infinite, right? And the second term gonna be, again, we have minus 1 per s and 1 per e power 0. Is it correct? It should be. It should be. So here, this term, it's gonna be 0. Minus gonna be plus 1 per s, and this term equal to 1. So the Laplace transform of unit step function equal to 1 per s, equal to 1 per s. And for ramp function, maybe if input force is equal to time multiplied by just a unit step. This is a ramp force input. Why I can say this? For this, if we need to plot the force varying against time, how can we plot a force varying against time? We have F is T. Actually, if Ft equal to T, we're gonna have something like this. But when it multiplied to a unit step, it means when time less than 0, the value of the function is gonna be 0. But when time more than 0, so maybe, I'm sorry, unit ramp function by this definition, the unit ramp function gonna have value equal to 0 when time less than 0, and the value of function gonna equal to t when t is more than or equal to 0. The Laplace transform of this, we begin from Laplace transform of t ut. The integral from 0 to infinite of e power minus st t ut dt. Again, maybe the meaning of the unit step is not so important because the limit of integral cover only the positive region. So this can be considered just a value of 1 multiplied to the rest term. But this integration may need by part technique. Let's assume u is different from the unit step, okay? By part gonna be u dv, v du. Let's assume u terms equal to t, which means dv gonna be e power minus st dt, and du dt v gonna be e power minus st and divide by minus s, right? The integral of e power minus st dt, we're gonna have e power minus st, and we divide by d minus s. So from the by part integral u dv gonna equal to uv minus integral v du, which means the original integration e power minus st multiplied by t integral u dv, t e power minus st dt integral u dv equal to uv, u and v gonna be minus t e power minus st divided by s and plus minus integral v du, but minus integral v du gonna be plus integral e power minus st divided by s and dt. Is that correct? Integral v du minus integral v du minus gonna be plus, and v du should be correct, and the limit of integration from 0 to infinite, this gonna be need to be considered from 0 to infinite, and this also considered from 0 to infinite. For the first term, when we consider t equal to infinite, it seems like we have 1 per e power infinite, which means 0. So the first term gonna be 0. For the second term, when t equal to 0, yeah, it's straightforwardly that t equal to 0. So by take the limit, the first term is 0. And for the second term, again, we have e power minus st. dt is for the integration, but s is just, it can be considered as a constant now. So we have 1 per s integral of e power minus st dt, which means we have minus s square. And the limit of integration from 0 to infinite. So when t equal to infinite, it's gonna be 0. And when t equal to 0, it's gonna be minus 1 per s square, right? So for a ramp function, the Laplace transform of a ramp function is equal to 1 per s square. Come back to the unit step. Laplace transform of a constant 1 equal to 1 per s. Laplace transform of t power 1 equal to 1 per s square. I think by now you can imagine about a parabolic function. Laplace transform of parabolic function. Do you have any idea for Laplace transform for parabolic function? For unit step, Laplace transform is 1 per s. For unit ramp, Laplace transform is per s square. If we increase the power of the function to be a parabolic function, Laplace transform gonna be 1 per s power 3. And if we done with the ramp function, I think sinusoidal function is a little complicated. Before the break, we may continue for just exponential decay. Exponential decay means maybe if the function have a decay function and multiply by again unit step a decay function, Laplace transform of exponential decay, gonna be integral from 0 to infinite, or we begin from e power minus st, and then we continue with our function. Yeah, again, unit step function. When we consider the limit of integral, this thing has no meaning. It's just one constant, a unit 1 multiplied to the rest term, and we can combine the terms to be e power minus s plus alpha t dt, and the integration of e power minus constant multiplied by t gonna be e power minus constant and divide by minus s plus alpha, and the limit of integration time from 0 to infinite. When time equal to infinite, this term gonna be 1 per e power infinite, which is 0. And the second term gonna be e power, when time t equal to 0, e power minus 0, e power 0 is equal to 1. So in this case, the Laplace transform equal to 1 per s plus, n alpha. For exponential decay function alpha, Laplace transform equal to 1 per s plus alpha in this case. Tired? Should we continue with the sinusoidal function first before the break? Yeah, I think we can. I think we can. Sinusoidal function, right? Maybe sinusoidal function means if we need to obtain a Laplace transform of cosine omega t, maybe sine omega t. We begin from Euler identity. E power j theta equal to cosine theta plus j sine theta. E power minus j theta. Maybe you may consider this as j and minus theta. Cosine theta and cosine minus theta is the same. Sine theta and sine minus theta gonna be minus sine. So do you have any idea if we need to compose cosine theta in the terms of exponential function? Equation 1, equation 2. If we combine equation 1 and equation 2, what we have, if we combine equation 1 and equation 2, what we have gonna be 2 cosine theta equal to e power j theta plus e power minus j theta, which means cosine is equal to positive a complex exponential and the negative angle 1 and divide by 2. How about when equation 1 subtract by equation 2? Equation 1 subtract by equation 2, we're gonna have 2j sine equal to e power j theta minus e power minus j theta, and psi, when we need to write in the term of the complex exponential, we can compose it like this. I introduce from here because when we need to obtain a Laplace transform, we know that we need to obtain an integral from 0 to infinite of e power minus st and cosine omega t dt. If you use a direct method, you may need to find an appropriate by part integration to separate the term of exponential and the sine or cosine sinusoidal function. But if you apply the trick of the Euler identity, maybe we can simplify the problem. Cosine omega t gonna be e power j omega t plus e power minus j omega t divided by 2 dt. And okay, we have 1/2 integral 0 to infinite, and we combine the term. The common term is time t, right? E power minus s and minus j omega t, and dt, and the second integral gonna be e power minus s plus j omega t dt. I think until now it's not a problem for you. You already know how to finish this derivation, but we will do it together. E power a constant multiplied by t. The integration gonna be e power minus s minus j omega t divided by the constant, and don't forget the limit of integration from 0 to infinite. Similarly, in the second term, we still have e power s plus j omega t, and divide by minus s plus j omega, and from 0 to infinite. And almost done. When time equal to infinite, e power minus infinite is 1/e power infinite is 0. Minus gonna be plus, and s minus j omega, and e power 0 1. Again, for here, when time t equal to infinite, e power minus infinite 1/e power infinite gonna be 0. Minus gonna be plus s plus j omega, and when time t equal to 0, e power minus 0, e power 0. Oh, why it's still difficult? Oh, okay. So we have different denominator, right? We have different denominator. So we need to make the common denominator to be s minus j omega s plus j omega. If we need to make the common denominator, it means the first term here need to multiply by s plus j omega. And this one need to multiply by s minus j omega. And finally, we have 2s divided by 2, which means we have only s, and s square minus j square omega square. For cosine, Laplace transform of cosine function, we can see s divided by s square plus omega square. Maybe if you have time, I would ask you to try Laplace transform of sine omega t. By using this Euler identity, and it's similar to for cosine because it's gonna have the same denominator, but the numerator for cosine we have a Laplace s, but for the sine we're gonna see the omega here. Try to check, derive this and confirm if this is true or not. Okay, we're gonna continue on the second half, but let's have 10-minute break. And please come back by 2:30.